Good afternoon, students. Today we will do a worked example of n non-interacting spins in a constant external magnetic field. Now, this is going to be a demonstration of how we compute physical properties of interest using statistical mechanics. And the working example that I have shown is spins in a magnetic field. So, you could think of these spins that are up and down in a magnetic field that is uniform and pointing out some direction, let us say the z axis. I can choose z axis to be anywhere, but I am just showing the magnetic field to be along this direction, that is my z axis, and this is like a constant magnitude in the direction of z axis. So, you can take n such spins, and for this system we can compute the magnetization of any given realization, okay, as I am going to say that let us take a microstate nu, okay, and if you want to write down the magnetization under constant temperature and constant field, this is nothing but just summation over all these spins, the individual magnetic moment. So, I am going to take mu as some magnetic moment per spin into the excitation of that spin. Now, this is going to be a system where the values of excitation can take anything between minus s to plus s. These are basically 2s plus 1 values. So, this is not s equal to half or spin half system where you can only take up minus 1 and plus 1 for the mi's. Here s could be 3 by 2, 5 by 2 or any large number, and this essentially gives your excitation values of minus s to plus s. Okay. So, it is not restricted to spin half system. I can take it the spin to be s, and so if this is for a spin s system and I have taken n such spins. Okay. So, the mi's, that is the excitation of each spin, can assume values between minus s to plus s, total 2s plus 1 values, and what I have written here is nothing but the magnetization of the some nth microstate. Okay. So, you can call it as the of magnetization of some microstate nu, okay, which is a label of a microstate. Now, what is meant by a microstate here? As you already know, microstate is nothing but specified values of these excitations. Okay. For example, you can take one microstate can be specified as m1 equal to 4, m2 equal to 3 and so on and so forth, and mn equal to some minus 2 whatever. So, this is one microstate. You can specify another set of values . So, this way you can set up a large number of microstates. Each one of them is nothing but the set of particular values of mi, okay, which means I can also call my microstate as nothing but a set of mi's. This is my label microstate. Okay. Having said that, I can identify the energy scale of the problem, which is the first thing to do. If you want to set up statistical mechanics, you have to set up the energy scale, and the energy scale is basically the Hamiltonian or the total energy scale. And since these spins are non-interacting, there is no internal Hamiltonian in the system. There is no interaction, nearest neighbor interaction between the spins. All these spins have is basically a coupling to the external magnetic field. So, the total energy scale is nothing but the magnetic enthalpy of the system. Okay, that is my energy scale. So, I am just going to write down the magnetic enthalpy as minus Bm. Okay. So, if this is the Hamiltonian of the nth microstate, then it is just minus B times Nu, okay, also called as the magnetic enthalpy. There is no other scale in the problem. The spins are non-interacting. I think I have already mentioned this. Yes, the spins are non-interacting. So, you do not take an icing like model where spins have a nearest neighbor interaction, which is given by a coupling constant J. There is no such J. The spins can only talk to an external magnetic field and can align parallel or anti-parallel to the field. So, the energy scale of the problem is nothing but the magnetic enthalpy, which is this. If you want to write down explicitly, you can say, okay, my nu is nothing but the set of excitation. So, that is the Hamiltonian of this particular microstate given as minus B times the instantaneous magnetization, which is nothing but the set of values of in our nu notation. Okay. And this is nothing but minus B times, I have already written what is the magnetization, which is summation over all degrees of freedom mu times Mi. So, I am going to pull out mu because it is a constant, and so mu here is nothing but magnetic moment per spin. Okay. So, you sum over all the spins along with their excitations, you get the total magnetic moment. So, this is just a summation over I going from 1 to n, the total degrees of freedom in your problem of your spin excitation. This is my magnetization of the certain microstate. So, the MIs that I take here in the summation are the MIs that are fixed by the microstate, okay, like I have shown here. Fine. Once the energy scale has been specified, in this case it is the magnetic enthalpy, I can ask meaningful questions. I can ask questions as to what would be the partition function of the system. The first important object that you construct on any physical system in statistical mechanics is the partition function, because once you have the partition function in your hand, you can do a lot of things. For example, if you have the partition function, I will call it as the Gibbs canonical partition function. At constant temperature and magnetic field, you can also call constant number of spins. Now, with this, if you compute the partition function, you can compute, for example, Gibbs free energy of the system. Okay. So, this is now development of thermodynamics. So, you can compute Gibbs free energy of the system as a function of B and T. Now then, with the Gibbs free energy, you can compute very interesting properties. You can, for example, compute what is the magnetic susceptibility of the system. This is a quantity that will depend on the system, whether it is close to a phase transition or not, and near to the phase transition there will be large values of magnetic susceptibility. It will sort of diverge, indicating a second order phase transition. So, magnetic susceptibility is an important quantity that one often constructs magnetic systems. So, chi, which is defined as the rate of change of magnetization as a function of applied field for very small values of field. This would be like if you want to expand magnetization in powers of the field, then the leading term of that expansion will be the susceptibility, the Taylor expansion of magnetization. Okay. So, to linear order, the rate of change of magnetization as applied field for very small values of field gives you the susceptibility of the system. And you can show that this susceptibility is a measure of fluctuations in magnetization. See, we are not controlling magnetization in this system, we are controlling magnetic field, temperature and number of spins. Now, the only way you can do it is to allow for magnetization to fluctuate. So, you can also connect this susceptibility to fluctuations in magnetization. It is like saying that in a canonical ensemble, when you had a gas in contact with a thermal reservoir, you kept number of particles, volume and temperature to be fixed. You could only keep temperature fixed by allowing an exchange of energy with the reservoir. So, the fluctuations of energy with the reservoir was a directly shown to be related to the heat capacity at constant volume. So, in some sense our susceptibility is also a measure of of fluctuations in the magnetic field, and it will be nice to compute this quantity. Another quantity that you can compute is basically the heat capacity at constant fields and magnetization, which means I would like to compute what is heat capacity at constant magnetic field and heat capacity at constant m. Right. So, now we will compute the partition function first and then compute the remaining physical properties. So, let us start with the partition function. So, the partition function here is nothing but the summation over all degrees of freedom. You can also call it as a trace, and the Boltzmann factor, which is e raised to minus beta into the energy scale of the problem. So, I have taken the energy scale which depends on the microstate, and I know this energy scale, which is basically e to the power minus which now becomes e to the power minus beta, and energy scale itself is minus Bm. So, the two minus multiply to a plus, and you get nothing but summation I going from 1 to n mi. The mi's here are picked up from the specified microstate in the summation. Okay. You have to sum over all microstates, and for each microstate whatever mi's you pick up, you have to use that in that summation, okay, and then add up to a next exponent and so on and so forth. Sum it over all microstates, you have the partition function ready. Okay. So, I can also write this as just summation over all microstates e to the power beta b into magnetization of the microstate. and this is because the magnetization of a particular microstate is nothing but summation over all degrees of freedom mu times m I. Okay. So, the preceding equation, which is this, allows us to write down the average magnetization. I can write down the average magnetization which is nothing but m, or you can just call it as m, okay, or within angular brackets, up to you. It is nothing but summation over all the microstates, magnetization of the microstate, that is being summed over e to the power minus beta into the energy scale and I know this energy scale has already been written as beta b into mu magnetization of the muth microstate, which is a set of mi's, divided by our partition function, okay, because this is the normalization of the probability, that is all. Okay. The denominator is nothing but our Gibbs canonical partition function. Okay. So, I can write this as, just to extract the magnetization here in the numerator, I can write down the average magnetization as nothing but d over d beta b of the partition function divided by the partition function g, okay, which is my denominator, and this is nothing but d over the beta b of the logarithm of the natural logarithm of the partition function. Okay. So, just keep this result handy. So, I am just going to sort of call this as equation 1. Once we have the partition function with us, we can compute magnetization also, which is not on the cards, but then it is a byproduct, you can use it. Okay. So, let us continue with our partition function. So, our partition function at constant field and temperature was already computed up to this step. Okay. So, I am just going to copy this here, it already computed, pre-computed. So, let us just bring it down here. Okay. So, I can now split up these summations, because they are summations over the degrees of freedom, the microstates. I can rearrange this in the form that simply the exponents that are added up become now products. Okay. And for the each I that I have taken outside, I can take my mi's to go from minus s to plus s. Okay. I will sum up over all these exponents. Okay. Please recall that our excitations are from the set minus s to s. 2s plus 1 values. Okay. Now, you can see this summation that is inside. For each I that is fixed by the product outside, you take the same values of mi minus s to plus s and compute the sum, which means I can simply compute it for one value of I and raise everything to the power n. Okay. So, this is now a simple task of just taking some variable m going from minus s to plus s e raised to beta b mu m, and you simply raise the entire thing to n, because you do it repetitively for each I, the same task, which is like doing it for one I and raising the entire thing to power n. Okay. And we can, for the sake of convenience, I can take the factor beta b mu as some g, because I do not want to write 3 symbols every time. So, this is nothing but summation m going from minus s to plus s e to the power g m, the whole thing raised to n. This is my partition function that I am going to compute. Is that okay? So, then I can write down my partition function as nothing but if I expand it, I will get terms, I will write down a few terms here. So, let me write down the terms here. I will be getting e to the power g s plus e to the power g s minus 1 all the way to e to the power g plus m equal to 0 will give me 1 plus e to the power minus g plus e to the power okay. So, I need some space here. Let me write down in a conserving space. So, suppose the first term I will write down from the positive side, this becomes e to the power g s plus e to the power s minus 1 all the way to e to the power g plus 1 plus e to the power minus g plus okay. Fine. And the entire thing is raised to the power n. Okay. So, you can now look at we can club this term and that term, we can club this term and this term, you can club this term and this term. Okay. You will be left out with just one. So, you can write this as one plus, so I am not going to write 1 first, e to the power g, okay, club these two, then you can write down e to the power twice g 2g all the way to that would be the last term. Okay. So, then you can call this entire thing as 1 plus twice cosine hyperbolic g plus twice cosine hyperbolic 2g all the way to twice cosine hyperbolic sg, the entire thing raised to n, okay, by using the formula for cosine hyperbolic. And I am going to take a factor of 2 outside. So, this will make me 2 raised to n into 1 by 2 plus summation some, we can take some variable, let us take let us take I going from 1 to s cosine hyperbolic gi, the entire thing to the power n. This is my partition function for constant field and temperature. Okay. We can do some simplification here itself. Let us see if we can simplify this further. Yes, we can. So, we can write down this cosine hyperbolic okay, I could have simplified it there itself, but okay. So, I can write cosine hyperbolic gi as e to the power gi plus e to the power minus gi over 2. Okay. What I am trying to do here is, because I do not think we need the entire summation up to s. Okay. So, I am going to approximate the partition function, if you want to call it if you want to call this as an approximation. So, let us approximate this. I do not want entire sum up to s. So, certainly I can do this approximation in the limit of small fields, which is what is required, right, which is what is mentioned. So, we are taking a field which is small enough, okay, and for the small enough fields I want all these quantities to be computed: partition function, G, susceptibility, and heat capacity. Okay. So, let us try to compute this partition function in the limit of small field. Okay. Otherwise, I have to retain all terms in the summation, but let us say if the field is small, then we can certainly do better. So, let us see if we can so this can be written as so e to the power gi plus e to the power minus gi by 2 can be written as, so I will take the 1 by 2 outside, and write down this as 1 plus gi plus gi the whole square by factorial 2, and for the minus gi I will write down 1 minus gi plus gi the whole square by factorial 2. Okay. So, I can easily see that all the odd terms will cancel and the even terms will add up. So, if I do not add terms beyond order G4, then I get this. This is 2, do not confuse it for anything else. So, I am going to add 1 and 1, okay, that is going to give me 2, plus I am going to add gi square. So, that is going to give me g square I square, okay, because there is a factorial 2 in the denominator, okay. And so what I get here is basically the next term would be order G4 that I am going to drop, okay. Now I am going to drop terms of the order G4 and above, because G, if you recall, is mu b beta, okay, and this goes to 0 . I am going to write down that for small b or small values of field, G square G4, I am going to write down that we are dropping terms of the order G4 and above, okay. Small field approximation. Like I said, I want to do something, I want to drop the summation. It is not dropped yet, but we will drop it in another step. So you can drop the terms of the order higher than 4, and then this summation becomes 1 by 2 so half into 2 is 1 and you are summing it s times, so it is just s, okay, plus I will take 1/2 outside and call this as summation I going from 1 to s. In fact, I will take G also outside, G square also outside, okay. So G square by 2 I will take outside, and what I will get is basically summation I going from 1 to s I square, and the entire thing is raised to the power n, fine, okay. Now sum of first s squares is already known, okay. You know that sum of first n numbers is n into n plus 1 by 2, sum of first n squares is n into 2s plus 1 into s plus 1 by 6. So simply substituting the known result of the sum of first s squares it is nothing but s into s plus 1 into 2s plus 1 over 6, okay. So you can try and you can check, suppose you take s equal to 3. So what you have for the sum is basically 1 plus 4 plus 9, which is 14, okay. And what is your right hand side? It is 3 into 4 into 7 by 6, which is also 14, okay. So our formula is correct, just verified, okay. So let us call that this is a rough work. And let us come back to our partition function. So our partition function is now so we are doing all this hard work because I want to write an approximate formula for partition function at small field. Plus s plus g square by 2 into what I have just cooked, s into s plus 1 into 2s plus 1 by 6. So 6 into 2 is 12, okay. So this is g square by 12. fine, entire thing raised to the power n. And this is the partition function for in the small field. Okay. Otherwise, you have to take this full partition function which is here. Okay. So, if you have to write down the partition function for any field, then this is your expression. You can't use that approximation that I have used, but you say okay, my magnetic field is small. Okay. Then this is the approximation. So, now you can use this approximation and compute the value of your various thermodynamic properties. Okay. So, for example, the first thing that you can compute is the Gibbs free energy. Okay. So, the Gibbs free energy, as we know, will now be a function of the field, and we know from the statistical mechanics discussions that there is a bridge between microscopic world and the macroscopic observations, and that bridge gives us the bridge that gives us the value of the Gibbs free energy as minus kT ln our partition function. Okay. Now, we will do it again for an arbitrary field and small field. So, for the Gibbs free energy, I can simply use this value of our general partition function, and this is the value of the partition function here. Yeah, 2 raised to n into 1 by 2 plus summation cosine hyperbolic g I. So, I am just going to copy. Okay. This is a partition function. You have to take a negative kT ln of your partition function. Okay. So, let us do that, it is very simple. So, what you can do here is nothing but minus kT, and you can simply take ln of A into B as ln A plus ln B. So, what you get here is just n ln 2 plus n ln half plus summation I going from 1 to S cosine hyperbolic g I. Okay. Fine. What I have done here is nothing but used the fact that ln A into B is ln A plus B. Okay. So, now you can already do a few things. So, you can now use the approximation for the Gibbs free energy that we have worked out of the approximation the partition function that we have worked out. Okay. So, for small b, so this was for any field. Okay. So, in the small b approximation, so we can write down however, for small b we have a ready made approximation for the partition function. So, we can use that approximation and compute the Gibbs free energy. So, I can write down my G as negative kBT of the and the logarithm of the partition function that is already pre-computed here for the small field approximation, which is I am just going to, since I am lazy, I am going to copy this entire expression and simply paste it here. Okay, minus kt ln of my z. So, this bracket here is corresponding to this bracket and this bracket here is for this bracket. Okay. So, let us do this calculation and so what you can do here is the following. So, you can take minus kbt and logarithm of this 2 will give you a common prefactor of n outside, because both these terms that are multiplying are raised to n. So, I can write down this as and now I can write down inside the bracket as ln 2 plus ln of half plus s plus g square s into s plus 1 into 2s plus 1 over 12. Is it okay? And now what I am going to do is yeah, let us combine these two logs, see what we can do. So, I can get log of okay. And then, so I have just multiplied 2 throughout, and what I am going to do is basically take 2s plus 1 also common. So, this becomes minus kb t n and write it as so just 2s plus 1 if I take out. So, what I get is basically ln of 2s plus 1 plus ln of g square s into s plus 1 over 6. And this will be, yeah, there will be a factor of 1 that I have missed. So, this will be okay. So, let us see if I multiply this. Okay, I am getting that second term first and then I am getting the first term also. All right, now we can sort of give some names to these terms. Okay, so what I can call here is basically So, this is my G at some magnetic field. Okay. So, the first term here has no magnetic field dependence. So, I am going to call this as G at 0 magnetic field without magnetic field plus or minus n kBt ln of, I am going to write it as 1 plus G square S into S plus 1 over 6. Is that okay? Where I have just used this nomenclature that the free energy at 0 field would be just minus n kBt ln of 2s plus 1. I am allowed to do this because just that is the first term is field independent. So, I am just calling it as G0, some arbitrary reference of the free energy. Because of state function, so its reference is arbitrary. I am calling this as the arbitrary reference. The next term which depends on field through this factor called G is called as the field dependent part. Okay. So, if you take the difference of Gb and G0, that would be the field dependent part of the free energy. Let us call this as the some equation number, let us call this as 1. And noting that for small x, by small x I mean when x is much smaller than 1, I can always write down ln of 1 plus x as just x. Actually the correct expansion here of ln 1 plus x is for small x I know that the leading term will be definitely ln 1 which is 0, okay, because you are expanding around 1. So, if x is 0, ln 1 plus x is ln 1 plus x times the derivative of ln x, which is 1 upon x at x equals to 1, okay, plus x square by 2 factorial 2 into derivative of 1 by x, which is minus 1 by x square at x equals to 1 and so on. So, what you get here is nothing but x minus x square by 2 and so on. Now, I have taken the limit x to be much less than 1. So, I am going to drop this to 0 and simply say that ln 1 plus x is very close to x, not a bad approximation. So, this term here can be just written as G square into S plus 1 by 6. Okay. So, I am going to rewriting 1. So, rewriting 1 with the approximation that G square into S plus 1 by 6 is much smaller than 1, because our G is already which is the magnetic field. If you take square of that, it is much smaller than 1. Okay. Okay. So, definitely G square into S by 6 into S plus 1 is also much smaller than 1. So, I can write down this entire equation as nothing but G at field is equal to G 0 minus NKT into G square into S plus 1 over 6. Is that okay? And definitely here I have dropped terms of the order b to the power 4 and above. So, this is my approximate Gibbs free energy in the limit of small fields. Of course, this approximation is valid only valid if field is small, if you take fields to be large, then you have to take the entire series. So, this is the Gibbs free energy that we have computed. Now, we can compute important objects such as magnetization. So, let me see what is on the agenda. So, we have to compute the next topic is to compute magnetic susceptibility, okay, chi. So, the magnetic susceptibility can now be computed by looking at this expression, a very important expression that I have derived. Okay. So, I am going to call this as equation 2. Okay. So, this is the value of the Gibbs free energy and the magnetization, the thermodynamic magnetization, this is thermodynamic in nature. This is not the instantaneous magnetization. Okay. So, you can compute this from appropriate derivatives of the Gibbs free energy, and we have already shown that this average magnetization is nothing but d over d beta b of ln partition function. Okay. You can go upstairs and refer to that discussion. Yeah, look at equation 1 here. Okay. So, it can be very easily computed. I know that my logarithm of the partition function is already related to the Gibbs free energy. Okay. So, this is already equal to minus beta into the Gibbs free energy because of that bridge between microscopic world and the macroscopic observations. So, I know already that minus one over beta ln partition function is related to the Gibbs free energy. So, I have simply substituted that here. I can knock off beta. So, this is just minus dg over dB. Okay. This is my magnetization, and I have used the value of the Gibbs free energy that is just computed for small fields. Okay. So, I just computed for this small field. I can just substitute, say the leading term has no dependence on the magnetic field. The dependence comes only from g square. So, I will substitute that here. Here for g, and remind all of you that we are using this, we can only use this for small b, okay, as b goes to 0. Our approximation of g is applicable only in the small b, which means the magnetization that I am going to construct is also for small b, because I have used that value of g here. So, you can knock off these two minus signs and put sorry, yes, of course, I think I was supposed to copy it, but left it upstairs. Okay. So, a lot of things can come out, n k b t into s plus 1, okay, divided by 6, and of course, our g is mu b beta. So, mu square beta square will also come out, and b square is differentiated to twice b. So, you can knock this off with a 3 here. In fact, you can write down just as b by 3 as the factor. Okay. So, this is the value of the magnetization, thermodynamic magnetization. So, you can see the larger the field, larger is the magnetization, and the prefactor which is essentially constant. And also another thing you see here is that magnetization has to be an extensive property, and it is because it has an n inside it. So, it is both extensive as well as it scales with the magnetic field that is applied externally. So, the next object that we can determine is the susceptibility, I believe, which was on the cards. Let us go up and check. Yes. So, the next object is the susceptibility, and as I said, susceptibility is basically, to first order, it is the derivative of magnetization with respect to the external field as the field is taken to very small values. Okay. So, the third object is the magnetic susceptibility of our n spin system. So, it is defined as the derivative of the magnetization over field at small values of field. Okay. So, we can compute this. Since we already have m over here, I can simply take its derivative at small values of field and get the value of susceptibility. Okay. So, or what I can do here is take the not take this approximated value of m and compute m, okay, from the Gibbs free energy. So, I can write this as d over dB, and m itself is minus dg over dB, okay, at b equals to 0. So, basically what I am going to do is nothing but minus second derivative of free energy with respect to field at b equals to 0. Okay. Either way you will get the same result. So, you take the derivative here. So, that is the value of the susceptibility as the field goes to 0. Okay. And finally, we can compute what is called as the heat capacity at constant field. Okay. So, you can compute the heat capacity at constant field, magnetic field, by simply taking the temperature derivative with respect to, since we are taking a constant field derivative, it has to be a partial derivative of the energy scale in the problem at constant field. Okay. So, the energy scale in the problem is just the magnetic enthalpy, which is minus Bm. Okay. So, it is straightforward. You can take the field outside because it is held constant, and this is just the temperature derivative of the magnetization, which has already been computed for your ease over here. Okay. So, if you look at this temperature derivative, what you get here is nothing but okay. So, if you take the temperature derivative here, I am going to just write as minus B d over dt of this whole quantity Notice that there is a beta square here. Okay. So, what you are going to do here is either you can convert the temperature derivative into beta, or you can do it with respect to temperature, both are fine. So, what I am going to do here is see that I have a 1 upon kT here. Okay. So, this simply becomes minus B. I will take all the terms that are constants n I will take out all the constants first, n into s plus 1 mu square, this becomes b square over 3, okay, and d by dt of 1 upon kBT. Is it okay? B becomes b square, kT into beta square is just 1 upon kT, and s into s plus 1 comes outside. So, what I will get now is basically b square n s into s plus 1 mu square over 3 kb t square. Okay. So, I can now sort of call all these things as some kind of a constant which does not depend on temperature or the magnetic field. Okay. It is a constant which is only extensive in nature, it scales with only system size or n. So, I will say that my heat capacity at constant magnetic field is basically some constant which is a system size dependent constant into b square by t square, or it is proportional to b square by t square. Okay. So, it is an extensive constant, but it is proportional to b square divided by t square. And how about heat capacity at constant magnetic field? Again we can do the same logic, we can take the partial derivative of the energy scale. There is only one energy scale in the problem, that is the magnetic enthalpy at constant magnetization. Okay. Now, this is interesting. If you do this derivative, you can of course, the magnetic field is held constant. So, when you do the chain rule, you can write it as minus b into dm by dt, and that is 0 because you cannot change magnetization. You want to do this derivative at constant m, and plus m into d of minus b by dt, which is also 0 because b is held constant. Okay. So, because m is constant, the first term goes to 0 and b is the constant applied magnetic field. So, this is 0. So, you cannot you cannot hold magnetization constant in this system, and hence the heat capacity at constant m is 0. That would mean what is the energy required to change the temperature of the system keeping magnetization constant. So, you will say that this is 0 because the slightest amount of energy is applied, magnetization changes. So, I can now write down that heat capacity difference in the same vein as the Cp minus Cv of ideal gas. We now have Cb minus Cm, which is nothing but Cb, which is just some constant system size dependent into b square by t square. Okay. So, this is where we end our discussion. We have computed the partition function, then we have computed the Gibbs free energy, and from the Gibbs free energy we computed various thermodynamic properties such as the susceptibility, which I have already told is related to the fluctuations of magnetization. I leave that as an exercise, how to compute susceptibility from fluctuations, please do that, and heat capacities at both constant field and constant magnetization for our target system, which is n non interacting spins in a constant magnetic field.